Good evening. I'm an educator from Kepler Education, and this is the 10th video of the POTD series. So before starting off with the video, I would love to request our viewers about our targets, which is 150 likes, um, more than 100 subscriptions, and about 500 views. So today is a hard problem. There is a hard problem today. So before wasting any time, let us start with the problem. So the problem name is smallest window containing all characters. So you are given with two strings, S and P, and you have to find the smallest substring in S consisting of all the characters including duplicates of the string P. Return empty string in case no such substring is present. If there are multiple such substrings of the same length found, return the one with the least starting index. Now this condition is of no import. It's very easy to um, implement. We will just use less than instead of less than equal to. Let us try to find out the smallest substring in S containing all the characters including duplicates of the string P. For example, if the string is time to practice, and if the string P is TTOC, you see in this entire string there is a TTOC. There have to be. If there isn't, then you can't do anything, but there will be. I think it is given in a question that there will be an answer always. Anyway, so first to take this particular substring, you see this particular substring has all the characters TTOC. But when you come here, you find this particular substring also appears to contain all the characters, and its length is 3, 4, 5, 6, 6. Again, if you are careful enough, then you will find out very easily that this particular substring also happens to contain. Okay, sorry. This red one doesn't. Red one is not the answer. Red one is not the answer. Red one is not the answer. This red one might be the answer. You see, this is the answer, and its length is 2, 3, 4, 5, 6, 7. 7. Now, let us come to the second example. It is found out it is the smallest substring of 7 length, so you are returning this. Now, what are you doing? You are coming to this particular example, TOC. So if you come to TOC, you will find that this particular substring has TOC. Again, you will find that this particular substring also appears to contain TOC. However, if you were careful, and the length of this particular substring is 6. However, if you very carefully observe, then this particular substring also appears to contain TOC from O to T, this particular T. And the length of the substring is also 6. So in this situation, you see this particular substring starts at index something y, and this particular substring starts at index x, and x is less than y. In this situation, you will only return that substring which is appearing earlier in the sequence. So in your answer, you will say if the length is less than, then only update. If the length is less than equal to, that condition you will not take. So if the length is equals to the previous length of answer, you will not update answer. If it is equal to the previous length of answer, you will update answer, and your updated answer will be TOPRSC, which is given here. Now, sorry, how to solve this problem? How to solve this problem? You see, a very subtle hint has been provided in this question itself. A very subtle hint has been provided in this question itself, which is it is very clearly mentioned here that the word is clearly mentioned here, window. So this somehow brings the concept of sliding window. Now, how to apply sliding window? This time I will just use example, because this question will be, since it is a hard question, it will be very easy if I use example. Let us say this is the P string, and let us say the S string is. In every situation, there are two pointers in a sliding window algorithm, which is I, and the other one is J. J pointer moves first, I pointer moves left of J. So first, this particular thing, you have to keep a track of all the characters of the P string. You have to keep a track of all the characters of the P string, and how this can be made. Very easily, this can be made using map. So T you have stored 2, O you stored 1, C you stored 1. But there will be a problem. The problem is in CPP, if it is Java, then it will be done in O of one time. But in CPP, map takes O of logarithmic of n time for updation or deletion, plus it is an extra. It will be an extra overhead. You have to keep the map. So you have to make updation and deletion of 1. Now how can I do it? See, at max, how many unique characters might be present in this particular string P? There will be 26 unique characters, unique at max. See, you define an array of size 26. Forget it. I'll just write the necessary portions. I'll just write the necessary portions. So the string consists of, let me write in a sorted manner, C, O, and T. What is the index of C? It is 2. Index of O, 14. Index of T, 16. Hopefully I am right. 18, sorry, 18. So in the middle, how as many are there, all of them will be 0. These are indexes. So beneath it, I will write the count. Obviously. So you can understand that this is the second index. This is the 14th index. This is the second index. This is the 14th index. This is the 18th index. All the remaining positions will be 0, 0. And 2, see how many C are there? There are 1 C. How many O is there? There is 1 O. How many T is there? There is only 2 T's. Okay, this is the initial configuration. Now let us start iterating. T I M E T O P R A C T I C E. Let's start at J from T. First, you check, is T danger element, danger character. Let us define danger characters as the ones whose presence must be present in the S string substrings. That is the answer substring. That is the character which are present in T. So you understand, you need a very fast method to check whether this particular T character is present in this particular T or not. One very feasible way of this is to store a set. Of unique characters. Store a set of unique characters. It returns find operation, that is the string present in O of log n time, well within boundaries. The n value, the number of the length of the array at max can be 10 to the power 6, not array, the string can at max be 10 to the power 6. So we can proceed to of n log n type complexity. If it's 10 to the power 7 or 8, then I would have gone for n. If it is, since it is 10 to the power 6, I can go for n log n. So anyway. So first we check here. First we check this particular T. Is T present? The set is T O C. Yes, T is present. So you will reduce the value of T by 1. You go to I, not present. You go to M, not present. You go to E, not present. You go to T, not present. You go to, okay, oh, sorry. You go to T, it is present. You reduce it by 1 more. You go to O, not present. You go to P, not present. You go to J. Oh, sorry. O was present. What am I doing? O was present. You go to O and you see it is present. So you reduce this number by 1. We're reducing. We're finding out. We're reducing. Not present. C is present. Reduce it by 1. At this instance, you carefully observe. If you do a O of 26 time complexity operation, that is a linear search in this CNT array, let's say in CNT array, you see that all the danger elements are taken. You will see that all the danger elements are already taken. That is, there is no danger element, or there is no danger element which has a count greater than 0. That is, a current substring from I to J does not contain the current substring. It means that the current substring from I to J does not contain any number of danger characters, right? Because there is no danger character left. That is to be included in the substring. Therefore, this is a valid substring. We find out the length. The length is j minus I plus 1. You see it is small. It is smaller than s dot size, and so you take this particular in the answer value. You write time to your prac. Now you have to check, since it is possible. This particular substring is possible. You have to see if it is possible. To reduce the length of the substring and see if we can again have any substring which is kind of like still possible with a reduced length. So you start moving I. You see T is a danger character, but you're moving it out of the window. You're moving T out of the window. So the current substring has a T less So in the outside of the window, there will be an increase in the number of t outside of window. So you make it 1. Increment it by 1. Come here. I not a danger. M not a danger. E not a danger. Okay, okay. Before, oh, no, sorry. You come here. I come here. T come here. Now, your current window. Very sorry. Your current window is this one. Your current window. Sorry. Your current window is this one. And in this particular window, you can easily see. In this particular window, you can easily see that there is only one t. There is no two t's. There is no two t's. There is only one t. So this cannot be a valid substring. So you have to search for a valid substring. So you have to increment j. You have to increment j. You have to search for a valid substring. You can only increment I if you do not get if you get a valid substring, and you try to reduce the length of the valid substring and see if the substring can be made smaller, keeping its validity intact. You come to j. You see it is a t. So one more t included in the substring from the outside, one t reduced from the count. So it is now again a valid substring. You see all are 0. You're always doing this O of 26 crime complexity linear search in this counter and see if it is a valid substring or not. You see it is a valid substring. You start reducing this particular thing. You start reducing this particular thing. It is a valid substring. Start reducing this particular thing. So you come here. M not a I not a valid character. M not a valid character. E not a valid character. T is a valid character. Before that, while the I is moving, you see. So you see, this is a valid character. It is a valid thing. It is a valid thing. It is a very valid thing. It's a very valid thing. So your new length will be first when before moving I is still here before moving I. You see this particular substring. This particular substring is a valid substring. You take the length j minus I plus 1. You see the length is same as that of the previous one. The length of the window j minus I plus 1 is exactly equal to n as dot size. This particular length. So you will not update. You will not update. But whenever you move I to let's say m by removing this I, the substring now becomes this particular thing. At this moment you see the length becomes shorter than the previous one. At this moment, you see that the length becomes shorter than previous one. Previous length was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now the substring length suddenly becomes 1, 2, 3, 4, 9, and it is still a valid subarray. It is still a valid substring. It is still a valid substring. All are 0. So the length of the current window is less than that of the previous answer that we got. So METOPRACT can be a valid substring. You will remove it and you will make it METOPRACT. This is a shorter substring. Now I comes here, M is removed. You see, this is again a shorter more substring. It is again a shorter more substring. So you will update it. You will update it. ETOPRACT. You come here. You go make I come here. You see, it is still again. It is still again a shorter more substring. It is still again a shorter more substring. Still again a shorter, and it is valid. It's valid. You will make it TOPRACT. Now you come. I make I come here. One T moved to the background. So outside a window counter, number of t will increase. This is no longer a valid subarray now. You have to make it valid. So you have to increment j. Not a danger character, not a danger character, not a danger character. J moves out of range. Iteration is complete. So your answer consists. Your answer value is TOPRACT, and you will return TOPRACT. In the first, you will have returned TOPRACT. This is the answer. Now, if I say P is equals TOC. So I will down under the algorithm very quickly. TIMETOPRACTICE. Very well. So what will be the thing? COT. All are 1. The rest in the middle, all are 0. All are 0. So these are the characters that actually matter, or basically what I say is danger character. 2, 14, 18. You see, you start the pointer from here. T reduced to 0. But they are not 0 yet. Not valid. Here, again a T encountered. You will reduce it again by 1 more because this isn't just a number. So if you get one more T, this will increase to 0. But that will still be a very substring, right? I mean, if you get a T here, let's say. So after making this 1, 0 by J, and again J1 when it comes here, oh, it goes into the substring. It goes into the substring. So it becomes minus 2 from minus 1 when it comes here. When it comes to T, this particular T, it becomes minus 2. But when you're moving out, this minus 2, why it is significant? Why is it significant? When you're moving out, let's say when I is moving out, when I is coming here, it moves 1 T out of bound. It moves T to the background. So the number of T's in the background increases, but it increases from minus 2 to minus 1. This implies the number of T's in the outside is not greater than 0. So this implies there are still T's which are inside the window. Since it is minus 1, and it will require two more. It will require two more to make the number of t's outside as 1. So there are two t's inside the window still. So this is what it signifies. Basically, it signifies negative means number of t's. If it is negative x minus x, if it is minus x, it means x plus 1 t's are inside the substring. So moving one t outside by incrementing the I pointer will make x t's remaining inside the substring, and it is still something valid. If 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 the outside, okay, sorry, it is still something valid. It is still something valid because this particular value will be minus x plus 1, which is still less than 0. So it is still a valid substring on the inside. So let me start this example once again. J, it becomes 0. Not a danger, not a danger, not a danger, danger, it becomes minus 1. So there are two t's currently inside the window because 1 minus or minus 1 is equals to O comes here, danger, it becomes 0. P comes here, R comes here, A comes here, C, danger. You see, the entire thing in this entire array, nothing is greater than 0. Nothing is greater than 0. Therefore, there is no danger character outside the window. Therefore, there is no character of P outside the window. Therefore, all characters of P, duplicate or not, are strictly within window. Therefore, valid substring. So once you get a valid substring, you try to decrease the number of decrease the number. Now, answer value right now is TIM and TOPRSE. Right, let's see where it will go. Now I is here. You increment I, you make it 0. There is still one t inside the substring. So basically, since there is one t inside the substring, there is still the interior is again still a valid substring. It's still a valid substring. So it becomes IME TOPRSE. Since there is one t still inside, because 1 minus 0 equals 1, 1 minus 0 equals 1. There is still one t inside the window, and you require one t because TOC, the P, contains only one t. There is no duplicate for t. So yes, if there are duplicates inside, the window, then this value might get to negative, but that is no concern at all. So now the I comes here. M, not a danger character. However, this again reduces to METOPRSE. Then M comes here, not a danger character. This becomes ETOPRSE. Then it comes here. It apparently is a danger character, so it becomes TOPRSE. And this T increases. This T increases to 1. Okay, so no. This T doesn't yet increase to 1, increases to 1. TOPRSE, it becomes TOPRSE. T is already inside this thing, inside this answer variable. Not a window. It's still inside the window. Very sorry, still inside the window. You see, it is still a valid substring. You again try to decrease the length of the substring and see if this can be again remain valid or not. So it becomes 1, and once it becomes 1, it is invalidated. If it is invalidated, you will try to increase j, and you come to this particular substring, which has exactly same length as that of before. This becomes 0. Very sorry, this becomes 0, which has exactly the same length as before. But the length did not decrease, so you will not consider this substring. But you will move on. You make I come to P. And your new substring becomes this one. Okay, since I came to P and I is a danger character, so this counter for O will increase to 1. This is no longer a valid substring. You have to increase J. And now the J pointer went out of bounds. The iteration over. You cannot take any more substrings. So what is the value that's stored in answer variable? It is TOPRSE, and this is the leftmost smallest possible substring. Now I shall write the code. So first, what you will require? You will require a set, as I said. Then what will you require? You will require a count. You will have to initialize them first. Sorry, it will be P. Takes off log and type. And you have to map how many T's are there. You have to map how many O's are there. You have to map all these C's. So I'm going to do so IT minus A to get the index or to get the ASCII value. Or to combine the ASCII value and get the index for the array. Like the ASCII value of A is the lowest, and it increases in a chronological fashion and increases in a sequential fashion of a difference of 1 till IT. So the index of the array can be found as IT minus A. We will increment it. That is, if C has been found once, the value will be 1. If C has been found again, the value will be 2. Now your main work starts. First you will make answer equals S. Now this is the J pointer that starts. Okay, we will also initialize the I pointer. We will also initialize the I pointer. Now your sliding window starts. If it is a danger character, if the J is a danger character, if ST dot includes S of J, find the CPP residual function is find. That is, if it exists in this set, if I to this character, sorry, if S of J, if find S of J, yeah, S of J exists in the array. If it doesn't exist in the array, this value will be ST dot end. Since it is existing, so the value will not go to the end and will stop in the middle, but this particular S of J is existing, and this will not become ST dot end, the value. So if it is found, it is a danger character. So CNT S of J minus A minus minus. That is, from the outside I'm reducing the number of J outside the window, and inside the window I'm adding this S of J. So from the outside I'm removing S of J. That's why I'm decreasing. Now if it is a valid substring, you just have to send the counter array and see if all the values are less than 0 or not, less than equal to 0 or not. That is, none of the values is greater than 0. None of the values is greater than 0. So while none of the values of count is greater than 0, it's a valid substring, you will try and decrease it. But first, you will take it as the answer. You will take it as an answer. It is possible. It is a valid substring. You will see if it is an answer or not. Now you will try to reduce it. Now, if it is a danger character, then only you will remove it from the window and add it and increment it outside the window. If it is a danger character, so if it is a danger character, if it exists in the set, then CNT of S of I minus A, you will remove it from the window and you will add it outside. Adding it outside means incrementing the counter of outside characters, and then you will increment I. This is the entire sliding window procedure. After the sliding window end, as you saw, after the J pointer reaches the boundary, the answer variable contains the answer or the smallest leftmost substring that is to be returned. That contains all the characters of P. So return answer. So before going to time of space complexity, I will just write the isPossible function. isPossible function is a O of 26 time complexity linear search that will search if all the values inside the CNT CNT array is less than or equal to 0 or not. So basically int or bool, let's say bool. For let's say it is IT. Let's call it IT. The length of count is always, as you can see, 26. Okay, now let's come to the time and space complexity. So before coming to time and space complexity, let me just show you the code first. So this is the exact code that I've written. So let us, okay, first you will take the set and the count array, and you will insert the characters, unique characters of P array, P string inside the set, as well as you will find out the number of characters, number of each and every character that is present in this array P, that is, you will map them. Like C is present one time, O is present one time, T is present two times, and so on. First you will take answer as S. You initialize it, and this is the I pointer, this is the J pointer, it is always moving. If it is a danger character, then you will put the danger character inside the window, and you will decrement the danger characters count from the outside of the window. That is what I've done. So while this particular window is a possible subarray, substring, possible substring. So you will see if the length of the substring is less than the answer size or not, strictly less than the answer size or not. And if it is strictly less than the size of the answer that you already have, you will update it with the answer. Now, since it is a possible substring, you will try to decrease the length of the substring and see whether it is possible again or not. So if it is a danger character, if the I is present as a danger character, then obviously you will have to remove it from the window and send it back to the outside. So you will increment the number of the danger character on the outside by 1 unit and decrease it from the inside. So by decreasing it from inside is obviously implicable it will be increasing on the outside. So to increase the danger number of this particular danger character on the outside, you will just increment the counter for the current character or the current danger character. You will increase I and you will reduce the window size and see if it is again possible or not. Once the J moves out of bound, this ANS will contain your answer. Now it is strictly written that return empty string if no such substring is present. If no such substring is present, this while is possible count this particular line never works, because not no substring or no window is a valid window or a valid substring. That is answer variable does not get updated at all ever. So answer will always remain as S. Your answer will why cannot I just write it as this thing? Because if I write it as this thing, initially with this with an empty array, this condition will always fail. So I have to make it as maximum as possible. It is like it is exactly like when you are finding out the maximum value of an array, you initialize maxi variable with minus 199. Or the minimum variable of the array, you initialize the mini variable with 199. So I did the maximum that I could. So I repeated X. Yes. So if the size of answer is exactly same as that of size of S, I could have written ANS equal to S. That would also work, but I'm comparing the size right now. In that case, ANS equal to S, it is very evident, and you will return the substring none. That is, you will return the empty array, empty string. Else you will return answer. Now, as for the is possible function, I just told you, if all the values of the array of count is less than equal to 0, that is there is no character of P or the counter that is outside the window. So every character of P is inside the window. That means every character of P is inside the window. That means it is a valid substring or a valid window. So for a valid window checking, you'll have to see if you will go through all the characters of the array. If any one character is greater than 0, that means one character of P string is outside the window. So it is not a valid substring. You will return false. And if all the characters are inside the window, you will return true. And lastly, you will return answer. So let us compare this by time and space complexity from here itself. This sliding window. Okay, first this particular is possible function. This time complexity will be O of 26, and space will be O of 1 because you're not using any extra space. But in this particular question, at worst case, sorry, this time and space complexity I did it for the wrong position. Yes, it will be here. Anyway, let it stay. Who cares? So let's remove it. Now, yes, this ST. At worst case, this can take off n because all characters are unique. This is always off 26, as you can see. So this can be said as off 26. Space. I mean space. Now this thing will require of n log n time. Why? N for this, and for each operation you will do log of n. This will take off 1. So this will take off n log n time. Now this thing, as you can understand, it will take off n time. And this is off log n. And this is the most important part. Okay, these are off on operations. This will take some time. This will take off j minus I plus 1 time, but you can nullify it with off on because this particular situation will arise in a very small number of cases. When the window size is less than the answer. So it will either be a one time or a very few times. So we don't have to consider it. There is no point in considering it. It is not necessary to consider it. Negligible amount of time it will increase. But yes, this will take some time, but there's no need to take it into account. This condition is important. It's I plus 1 plus. This will take off and log n time. login time. This I plus plus is important. You see, when you're moving, the j is moving. Let us say here a value string has been found. You will move I in this manner, and j will remain constant. J will remain fixed. Here invalid string has been found. Now, when j moves, I stays fixed. And when I moves, j stays fixed. And when j moves, I stays fixed, goes out of bounds. So you can see at max, when j is fixed, I moves to n. I is fixed, j moves to n. Basically, I independently moves to n, and j independently moves to n. So on the worst case, this will take n plus n equals 2n time. So roughly, I can tell that the time complexity for the sliding window will take O of 2n log n time because of these log n's, because of these log n, because of this and this log n. So on an overall, the overall algorithm will take a time complexity of O of n log n plus O of 2n log n into O of 26. So basically time complexity is of n log n plus O of 2n log n into 26. This is the time complexity. What is the space complexity? O of 26 plus n. This is the space complexity. So this is the time and space complexity for this entire algorithm. So let us run and submit it first. Yes, it has run perfectly. Let us submit it. Yes, got submitted. So as you always, this entire notes will be present in our. Okay, I haven't provided you the code. Sorry, I'll provide the code first. Yes. So this entire notes will be available in our website. In the library section, resources tab, community library. Again, you have to log in. You have to log in to access them. And I'm starting to provide all these recordings, all these lectures in our website playlists as well. For each and every courses, if you go to the playlist, you will be able to find this particular YouTube lecture. So I think that's all for today. Please do make sure to log in to our website, as a number of logins are still a few. And if you, as before, if you wish to study at Kepler Education, then please put a comment at both the group chat, either the group chat of Kepler 22B in a community group, or in the comment section of this YouTube. So that's all for today. Thank you.